Hi there again, Gordon West, WB6NOA with Radio School, and congratulations, you're more than 3/4 of the way through your extra class training materials. 3/4 of the way through. And I know you're probably going, is this stuff sticking? Well, I did a little test on a student the other night that had just been listening to this portion of the audio course, and by golly, yes, it will stick. So continue to work with us. We're almost finished. I've tuned into PSK 31 and hooked up with a DX station on the other side of the world, and we're having a great time. And we're down here in the extra class portion of the band, and I know shortly you too will be coming up on the extra portion of the bands. All right, let's go ahead and take a look at E8A AC waveforms, talking about sine waves and square waves and sort of square waves and sawtooth waves and all those kind of waves. E8A01 says, starting at a positive peak, how many times does a sine wave cross the zero axis in one complete cycle? Well, starting with a positive peak, it goes up, through, down, and back, so it would cross through in one cycle 2 times. Now, be careful, 2 times, which is 360 degrees. What is a wave called that abruptly changes back and forth between 2 voltage levels and remains an equal time at each level? Well, that would be a square wave. And do you know what sine wave added to a fundamental frequency make up a square wave? What kind of sine waves added to them? They're called all odd harmonics. What sine waves added to a fundamental frequency make up a square wave? That would be all odd harmonics. And think of odd harmonics as 1, 3, 5, and 7. What type of wave is made up of a sine wave of a fundamental frequency and all odd harmonics? Well, odd, that's somebody that's pretty square, right? That would be a square wave. Now, the sawtooth wave is a wave with a straight line rise time faster than a fall time. Looks like a saw, or it could be the other way around. What type of wave has a rise time significantly faster than the fall time? That's called a sawtooth wave. What type of wave is made up of sine waves of a fundamental frequency and all harmonics? Not all odd, but all harmonics. That would be sawtooth. Odd harmonics, that would be the square wave. All right, do we have waves down? All right, let's take a look now at voltages. How much voltage do you get right out of your household electrical outlet? Oh, I know that, 110 volts. Wrong. 120 volts? Wrong. They're actually saying what is the peak voltage at a common household electrical outlet. Peak voltage. Now, if we were to measure that on an oscilloscope and look at the peaks, it would be 1.414 times higher than 120 volts. So 120 volts, which is average or RMS, multiplied by 1.414 will end up with 170 volts. So be careful. I misread it the first time. They're asking for peak voltage, which is different than RMS, which we just take for granted. How about the peak-to-peak voltage at the common household electrical outlet? Well, that's 340 volts. It is 120 times 1.414, which is 170. And since they want to know from the top peak to the bottom peak, we multiply 2 times 170, and that comes out 340. What's the average voltage? Another name for average is RMS, root mean square, of the household electrical power outlet? Well, the average is 120 volts AC. What is the average value of a 340 volt peak-to-peak pure sine wave? Well, first thing we need to do is take 340 peak to peak and make it just peak by dividing by 2. And then we multiply it to go from peak to average by, do you know what numbers we multiply it to go from peak to average? That's right, 0.707. Think of the old aircraft, the old 707. What is the equivalent to the root mean square value of an AC voltage? Well, the equivalent would be a DC voltage causing the same heating in a given resistor as the RMS AC voltage of the same value. Now be careful, they've got another answer. It says DC voltage, heating, given resistor, and it's as the RMS, not the peak, but the RMS AC voltage. So be very careful on your upcoming extra class test that you don't speed read the answers and go for the first one that starts out looking correct. Many times it ends up not correct. Always be sure and read all 4 answers and then make sure you've chosen the right one. What would be the most accurate way of measuring the RMS voltage of a complex waveform? Well, one way might be by measuring the heating effect in a known resistor. For many types of voices, what is the approximate ratio of peak envelope power, abbreviated PEP, to average power during a modulation peak in a single sideband phone signal?
When you can see the peregrines hatching their...
Now, notice as this station is transmitting that he's not on the air all of the time because of spaces in between each syllable. Well, for many types of voices, the approximate ratio of peak envelope power to the average power is 2.5 to 1. Now, depending on your modulation, now if you have a lot of background noise, that'll change. But normally, for single sideband, your transmitter is on an average of 2.5 to 1, which is the ratio of peak envelope power to average power. Now, in a single sideband phone signal, what determines the peak envelope power to average power ratio? Well, that would be the speech characteristics. So depending who you've tuned in, there's a real distant foreign station coming in down here in the extra portion of the band. Depending who you tune in, their transmitter may or may not be working hard on single sideband voice. Certainly if they click in the speech processor, the transmitter will be working harder. And if they have a lot of background noise, it'll be working much harder. In other words, it'll be heating up a lot more because they've got their transmitter constantly running, even with the background noises coming in. Now, there was a station with a speech processor. Here's another station with a lot of background noise working that transmitter. Now, do you hear all that background noise coming in?
Take it back in there and let them change it, and then the alternator went out.
Yeah, that transmitter's probably getting mighty warm. So, on a base station, make sure that you don't turn up the speech processor too hot. And mobile, always run without the speech processor, and ideally, a noise-canceling Heil microphone element will keep all that background noise nice and quiet. Now, one way to put in a better signal to the other stations, so it is nice and quiet, would be an amplifier. And they asked the question E8A16, the approximate DC input power to a Class B RF power amplifier stage in an FM phone transmitter when the peak envelope power output is 1,500 watts. Now, this is a strange question. I can't imagine anyone running FM at 1,500 watts out. But anyway, you can determine the input power by dividing peak envelope power output by the efficiency of the amplifier. All right, let's see now. What do we know about this? Well, the efficiency is normally rated in a percentage divided by percentage efficiency by 100 to get over to the decimal value. 1,500 watts peak envelope power by 0.6. Now, this you need to write down. 0.6 is the efficiency of a Class B amplifier, 60% or 0.6. Now, they don't tell you that on the question. You just remember B is 0.6. And the Class B is a bit more efficient than the Class AB amplifier. An AB amplifier is about 50% or 0.5. This is just B. So 1,500 divided by 0.6 gives us a power input of approximately 2,500 watts. Or for the common Class B amplifier, 2,500 watts in will normally provide about 1,500 watts output. Now, here's the formula to calculate peak envelope power. Peak envelope power is equal to power input DC times efficiency. And your efficiency would be 80% or 0.8 is the Class C amplifier, most efficient. The B is 60% or 0.6. The AB, we just mentioned, is 50%, and the Class A is a little bit less than 50%. So you need to know these for your upcoming test. The C, 80%, B, 60%, and AB, 50%, and Class A, a little less than 50%. Okay, let's see if you can do this question. What's the approximate DC input power to a Class AB RF amplifier if an unmodulated carrier transmitter is putting out 500 watts? Well, 500 watts, 50% efficiency would be 1,000 watts input because it is an unmodulated steady carrier. Period of a wave, that is the time required to complete one cycle. All right, now let's take a look at E8B. These are emission designators, and you'll learn a lot about emission designators by reading over my exclusive Gordon West Extra Class book, and that's the third of my series. And in the book, I show you the 3-digit ITU emission designators. Now, the first ITU emission designator, the first symbol represents the type of modulation of the main carrier. So the first is type of modulation, T. The second symbol is the nature of the signal modulating the main carrier, the N. So first is T, then is N. And the third symbol is the type of information to be transmitted. So be sure and remember these three. First one is the type of modulation, and then the second symbol is the nature of signals modulating the main carrier, and then the third symbol is the type of information to be transmitted. Now let's see what they ask on this first one. What is A3C? Well, A means amplitude modulation, just like the A is. And the number 3 means voice or usually an other analog information. And C for facsimile. C for simile. C for facsimile. So A3C is facsimile. And again, look in my book at all of the different designators. What emission is produced when an AM transmitter is modulated by a facsimile signal? Well, remember C for facsimile, that'll be at the end. A for amplitude modulation. So the answer is A3C. And they say modulated. So that would be A3C by facsimile. Facsimile transmission produces printed pictures by electrical means. How about F3F? Well, if you continue to watch television when you should be playing these tapes, you're going to get an F. All right, F3F. The F is for television, and the beginning F is for frequency modulated. So F3F is frequency modulated television. F3F. Keyword television. What type of emission is produced when an SSB transmitter is modulated by a slow scan television signal? Well, that's what it sounds like, and you'll find all sorts of slow scan activity down on 14230 and 14233. Great slow scan activity down there. They're always on 24 hours a day. Well, what type of emission is produced when an SSB transmitter is modulating this signal? Slow scan television. Well, single sideband always has sort of a jiggly sound, doesn't it? It does. Well, think of J for the designator beginning SSB. So J3F. And since we're talking about single sideband and television, there's the F. So a SSB transmitter modulated by a slow scan television signal is J3F. Now remember, if the first symbol of an ITU emission is designator J, representing a single sideband suppressed carrier signal. What information about the emission is described? Remember, that first designator is the type of modulation of the main carrier. Now, if the second symbol of an ITU emission designator is, let's say, 1, representing single channel containing quantized or digital information, what's this telling us? The second number is the nature of signals modulating the main carrier. And finally, if the third symbol of an ITU designator is, let's say, D for data, telemetry, or telecommand, this is the type of information to be transmitted. Okay, now let's talk and go on to a little bit of phase modulation, and let's go from SSB over to FM.
Go ahead there, Handsome Rich.
All right, how does the modulation index of a phase-modulated emission vary with RF carrier frequency, the modulated frequency? Well, with the modulation index of a phase-modulated emission, it does not depend on the actual RF carrier frequency. Has nothing to do with the frequency, but rather what's happening in the microphone. Now, in an FM phone signal having a maximum frequency deviation, and this is normal, of about 3,000 hertz either side, plus or minus 3 kilohertz of the carrier frequency, what is the modulation index when the modulating frequency is 1,000 hertz, such as the normal voice tone? Well, this is easy. Peak deviation over modulation frequency gives us the modulation index. Well, the peak deviation was listed as 3,000, and we don't double that. It's just simply 3,000, and it's divided by 1,000. So 1,000 into 3,000 goes 3 times. That is the modulation index. Now let's try another one. How about a maximum carrier deviation of 6,000 kilohertz, plus or minus 6, when modulated with a 2 kilohertz modulating frequency? No problem. 2 into 6 goes, again, 3 times. Now, the deviation ratio is a little different than the modulation index. Deviation ratio is equal to maximum carrier frequency deviation in kilohertz divided by the maximum modulation frequency in kilohertz. So they say, what is the deviation ratio of an FM phone signal having a maximum frequency swing of plus or minus 5 kilohertz and accepting a maximum modulation rate of 3 kilohertz? Now, we divide the maximum carrier frequency swing by the maximum modulating frequency. 3 kilohertz modulation frequency into 5 kilohertz frequency swing gives you a deviation ratio of 1.67. Deviation ratio is the ratio of the maximum carrier swing to your highest audio modulating frequency when we speak into the microphone. Now, there's different types of modulations. The latest is pulse width modulation. Why is the transmitter's peak power much greater than its average power for pulse width? Well, that's because the signal duty cycle is less than 100%. What is one way that a voice is transmitted in a pulse width modulation system? Well, a standard pulse is varied in duration by an amount depending on the voice waveform at that instant. And so catch that again. Standard pulse is varied by and it's not amplitude, but the duration by an amount depending on the voice. That's why they call it pulse width modulation. Which of the following describe the 3 most used symbols in an ITU emission designator? Well, that is, we've had it before, type of modulation, nature of the modulating signal, and type of information to be transmitted. The 3 most used symbols of an ITU emission, like J3E, J for type, 3 for the nature of the modulating signal, and E, the type of information to be transmitted. Now, if the first symbol of an ITU emission designator is G, representing phase modulated signal, what information about the emission is described? Well, G is, again, the type of modulation of the main carrier. In a pulse position modulation system, what parameter does the modulating signal vary? Well, in pulse position, the time at which each pulse occurs. So position is time. In a pulse width modulation system, what parameter does the modulating signal vary? Well, it varies, and this is pulse width modulation now, it varies the pulse duration. And how are the pulses of a pulse modulated signal usually transmitted? Well, usually it's a pulse of relatively short duration that is sent. A relatively long period of time separates each pulse. In an FM phone signal, what is the term for the ratio between the deviation of the frequency modulated signal and the modulating frequency? Oh, we know that. That's right, not percentage, not quieting, not FM compressibility. It is modulation index. And what is meant by deviation ratio? That's the ratio of the maximum carrier frequency deviation to the highest audio modulating frequency. Let's try one more numerical one. Easy one. Deviation ratio, FM phone signal, maximum swing of 7.5 kilohertz. Wow, that's wide. 7.5 kilohertz, accepting a maximum modulation rate of 3.5. If you had no clue what to do, first try division. 3.5 into 7.5 comes out 2.14. And if there is an answer that agrees with, you just gave it a try and it works out, take a look and get ready for that answer, but you might even try it backwards to see if there's another answer, and if there is, you have to make your best choice. But if you remember, little number into big number when we're talking about deviation ratio, as well as modulation index. Little number is divided into the bigger number. All right, that concludes our B section, E8B. 24 questions that we've just covered in the B section. And how many will be on the test out of E8B 1 through 24? Just one. And we've covered the E8A, and out of all those questions, only one will be on your test. Now we go to E8C, talking about digital signals, and a digital signal includes CW. That's right, Morse code is a digital signal. And we'll talk about digital signal information rate versus bandwidth and spread spectrum communication. What digital code consists of elements having unequal lengths? Oh, you know that one. That is Morse code. Now, what are some of the differences between the Baudot digital code and ASCII? Well, Baudot uses 5 data bits per character. ASCII uses 7. Baudot uses 2 characters as shift code, and ASCII has no shift code. And what is one advantage of using the ASCII code for data communications? Well, it's possible with ASCII to transmit both upper and lowercase text. Another fascinating area to add to your extra class expertise is digital communication systems for meteor scatter communications. When we don't have a normal meteor shower scheduled, we blast out CW signals called computerized high-speed CW at rates that sound like this. Is that amazing? This is computerized high-speed CW, well suited for meteor scatter communications at times other than during meteor showers. With your new extra class license, you're going to love these digital modes. Yeah, this will be sound to your ears, huh? Well, at least to your computer's ears. What type of error control system does Mode A Amtor use? Well, Mode A, the receiving station automatically requests repeats when needed. What type of error control system does Mode B Amtor use? Well, in Mode B, each character is sent twice by the transmitting station. Okay, back on CW. What is the necessary bandwidth of a 13-word per minute International Morse code emission A1A transmission? How wide is this transmission right here? From here to here, it is 52 hertz. Now, how'd you know that? I'm smart. Now, for CW, the baud rate is 0.8, fading factor 5. Therefore, multiply 0.8 times 13 words per minute times 5. So they ask 13 words a minute, 0.8, that's a given that you need to know for the test, times 5, that's the fading factor, times 13 words a minute, and it comes out 52 hertz. Wow, 52 hertz certainly has to be the most narrow form of transmission. Well, it used to, but now 31 hertz for PSK 31. Hear this? This is the most narrow, at least for right now, type of data transmission. PSK 31. And how many have a laptop computer or a home computer with a sound card? Wow, there are programs right now that allow you to receive what's being sent at PSK 31. Uh-oh, we have... You hear that? Two different digital modes, but believe it or not, both will survive and both will get through. Hear them? PSK 31 and sounds like Amtor. What is the necessary bandwidth for a 170 hertz shift 300 baud ASCII emission J2D transmission? All right, for this, the digital bandwidth is baud rate plus 1.2 times the frequency shift. So that would be 300, which they give you, plus 1.2 times 170. So for data, you need to remember 1.2, and it comes out about 500 hertz or 0.504 kilohertz. On the exam, they have it as simply 0.5 kilohertz. How about 1,000 hertz shift 1200 baud ASCII F1D emission? Same formula. Use a formula of, first of all, 1.2 times 1,000. That gives you 1,200 plus the 1,200 baud rate, and 2,400 is your correct answer. How about 4,800 hertz shift 9,600 baud ASCII emission F1D? Well, let's first do the addition, and that is bandwidth equals 9,600 added to 1.2 times 4,800. Just don't forget the 1.2. That's the only thing not listed in the question. And that comes out 15,360, or moving the decimal point 3 places to the left, 15.36 kilohertz. What term describes a wide bandwidth communication system in which the RF carrier varies according to some predetermined sequence? It's called spread spectrum. And up here on VHF, there's spread spectrum going on right now. And can you hear it? Not at all. Spread spectrum communications are becoming more popular on the VHF and UHF bands, and you probably didn't realize, but your little 900 megahertz spread spectrum cordless phone uses the same type of emission. The frequency hops in prearranged sequence, eliminating interference and eavesdropping. What spread spectrum communications technique alters the center frequency of a conventional carrier many times per second in accordance with a pseudo-random list of channels? That's called frequency hopping. Frequency hopping. What spread spectrum communications technique uses a very fast binary bit stream to shift the phase of an RF carrier? That's called direct sequencing. Now, be careful when they ask the words spread spectrum, the answer is usually not spread spectrum. If they ask wide bandwidth, yes, that's a spread spectrum answer. But if they say what spread spectrum communications technique, then it's another answer. So many times per second in accordance with a pseudo-random list of channels. Think of channels as frequency hopping. Bit stream to shift the phase of an RF carrier. Think direct sequence. And what controls the spreading sequence of an amateur spread spectrum transmission? That's a binary linear feedback shift register. Say that 8 times fast. A binary linear feedback shift register. What makes spread spectrum communications resistant to interference? Well, only signals using the correct spreading sequences are received. And what reduces interference from spread spectrum transmitters to conventional communications in the same band? Well, spread spectrum signals appear only as low-level noise in a conventional receiver. Now, some hams may argue that any kind of noise, low-level or not, is not good noise. So we'll have to wait and see what's going to happen to the future of spread spectrum when you get started with your extra class license. Spread spectrum. Can't hear it, but it's there.
Around the 8th of May, and then
The YL nets, I enjoy listening to them.
someplace else, and then ending up in Dayton. So you'll be able to visit.
And I hope you're going to go to the Dayton Amateur Radio Convention in May. This is Mecca. This is the biggest ham radio convention in the country.
It was so crowded and so.
Well, yeah, it's crowded, but there are hundreds of exhibitors. You should make it a plan. Dayton, Ohio, every May. Now let's take a look at E8D01. What is the term for the amplitude of the maximum positive excursion of a signal when we listen to this young lady on our oscilloscope tied into the radio? Well, it's called the peak positive voltage. That's the term for the amplitude of the maximum positive excursion of a signal. Think of positive, positive, positive excursion, positive voltage. What is the easiest voltage amplitude dimension to be measured by viewing a pure sine wave on an oscilloscope? The easiest one to measure is peak to peak. Now, do you know the relationship between peak to peak voltage and just peak voltage? It's 2 to 1. What input amplitude parameter is valuable in evaluating the signal handling capability of a Class A amplifier? Well, we need to look at its, for Class A, peak voltage. What is the peak envelope power output of a transmitter that has a maximum peak of 30 volts to a 50 ohm load as observed on an oscilloscope? Well, we multiply 30 times 0.707. Remember, the peak envelope power is equal to the average power output. The first step in solving this problem is to take the peak voltage and reduce it to average by multiplying 30 times 707. Now, average volts times average current equals average power, and they're looking for peak envelope power, so we have to change that around. That peak envelope power is going to equal E squared over R, or 21.21 volts squared divided by 50 ohms, and that comes out 8.99 watts, or 9 watts. Now remember, we started out with a peak envelope power seen on the scope as 30 volts into a 50 ohm load, and it comes out 9 watts. If an RMS reading AC voltmeter reads 65 volts on a sine waveform, what is the peak to peak voltage? Well, 65, all right? First, let's go 65 average to peak, and we do that by multiplying 65 times 1.414, and that comes out 91.91, but they want peak to peak, so we multiply 91.91 times 2, and that comes out 184, which is your correct answer. What would be the advantage of using a peak reading voltmeter to monitor the output of a single sideband transmitter? Well, that way it would be easy to calculate the peak envelope power output of that transmitter. An electromagnetic wave? Oh, they're all around us. That's a wave consisting of an electric field and a magnetic field at right angles to each other. And in my book, I have a great drawing showing you just that. And which of the following best describes electromagnetic waves traveling in free space? Well, changing electric and magnetic fields propagate the energy across a vacuum. Think of free space and vacuum, and that'll come up with the right pair of answers. Free space and vacuum. What is meant by circularly polarized electromagnetic waves? Those are waves with a rotating electric field, and that's what we need to work satellites. If you don't have circular polarization, listen to the fading that takes place.
By the way, my name is Frank, Bell Frank, Trot, DL, recorded on kilowatt.
Hear that?
B6NOA. This is before I'm the fast guy. Go ahead.
Yeah, typical satellite reception on a ham satellite without a circular polarized antenna. What is the polarization of electromagnetic wave if its magnetic field is parallel to the surface of the Earth? Well, remember, it's the electric field that determines polarization, so if the magnetic field is parallel, the polarization of the electric field, which they're looking for, is vertical. How about the polarization of an electromagnetic wave if its magnetic field is perpendicular, up and down to the Earth? Well, then the electric wave and the polarization of the wave is horizontal. And what is the primary source of noise that can be heard in an HF band receiver with an antenna connected? Well, hopefully we should hear this type of noise, which is perfectly normal, and yeah, that's atmospheric noise. And approximately what speed do electromagnetic waves travel in free space? Remember, a vacuum, that would be 300 million meters per second. Don't go for miles, but 300 million meters per second. And to ensure you do not exceed the maximum allowable power, and I know you wouldn't ever do that as an extra, what kind of meter should you use to monitor your output signal of a properly adjusted single sideband transmitter and probably that huge amplifier? You need a peak reading watt meter. And the average power dissipated by a 50 ohm resistive load during one complete RF cycle having a peak voltage of 35. Remember that formula? P is equal to E squared over R. So first of all, we have to do 35 volts down to average, 0.707. That takes it to 24 volts. 24 squared divided by 50 comes out about 12 watts. And how about the RMS reading voltmeter reading 34 volts? All right, 34, we first need to multiply, because they said it's an RMS reading voltmeter reads 34. And they want to know what the peak voltage is? Oh, that's an easy one. We multiply 34 times, remember going from average to peak? That's right, 1.414. Remember, going from average to peak, multiply by 1.414. Going from peak to average, you would multiply by 0.707. Boy, you're making great progress. Now, before I let you go to go out there and wash the cat. Oh, no, that's not all right. Not wash the cat, but brush the cat. Oh, okay. I'm sorry. Brush the cat and pet the dog, or with. Well, whatever you're going to do, don't go just yet, because I want to do a quick review. Now, there. Well, that's what happens when you get ready for the big review. So here we go with just a quick review for about 4 minutes to see all the great progress you've made. And then we'll let you go out and brush the cat and wash the dog. Remember that electromagnetic waves in free space go 300 million meters per second. And one of the exciting parts of extra class will be receiving electromagnetic waves, both short path and long path. And right now, as I'm recording this, drying off the wet cat that I meant to brush rather than wash, listen to what's coming in long path. This is really amazing. And listen to the echo, because I'm aimed long path, but still picking them up short path. Hear the echo? You are going to have so much fun on the extra class portion of the band. You really are. And we only have one more area to cover on our final audio cassette, if you're listening to us on tape cassettes. And that final area will be antennas. And then we have the big review. And the review will be going over those questions that in our classes we find that students know, but they somehow sometimes get tripped up on the exam because either they forget a keyword or they go for a wrong answer. So we're going to do a little precautionary observation of the question pool and cover this new pool in detail as a review at the very end of this audio course. So now put on your antenna hat because we're about ready to play antennas on the next and last segment of our course. And with that big antenna up at your new extra class station, you'll have a chance to work new operators, slightly dyslexic.
QC 10 meters. November 6 Oscar Sierra, November.
What's this?
Calling QC 10,
Q. He means CQ.
10 meters and standing by.
Well, you just got it backwards. Well, that's all. Well, anyway, you're going to have a great time working new and old operators out there on the airways with your extra class privileges coming up shortly.
Juliet Yankee 1, Juliet Yankee number 1, Whiskey Bravo 6, November Oscar Alpha, please come in again.
Wow, there's no telling who you're going to reach out there on the airwaves. So play this portion of the audio course over a couple of times and be sure that you've got signals and emissions down pat. Remember, you'll have 4 exam questions out of 4 groups out of E8 signals and emissions on AC waveforms, FCC emission designators, digital signals including CW and spread spectrum, and finally that peak amplitude, positive and negative, peak-to-peak values and measurements that we were just talking about. So this is Gordo, WB6NOA, and I'll meet you on our final course in preparation for your extra class amateur radio license.